Oh, so okay, so okay, let's get started. Did you have a good long weekend? Actually, in this semester, we have many holidays on Monday, but fortunately, we have Tuesday and Thursday classes. So I believe we don't have any canceled classes during this semester, right? Maybe I may cancel the classes because of my schedule, but we don't have any classes due to we don't have any canceled classes due to the national holidays. Okay, so before starting today's class, I will fix some what I learned in this course. So actually, if you see the score instruction, then actually in the old PDF document, not PDF, it may be in the old Excel document that summarize the RISC-V integer instruction, then you can find that the store instruction was SW, so store word, and then RS actually it was RS1 and RS2. But actually, I also I also made this document based on some materials what I found in on the internet, but it was wrong, unfortunately. So and then also I was not able to find some instruction format of the store instructions in the RISC-V instruction manual. But if you read the textbook, then you can find that actually store word starts with the RS2. This is the source register number 2, and then store instruction reads data from this source register number 2, and then calculate the target address using RS1 and immediate data, and it's the same to the load instruction. So if you see the load instruction, so you can find that this is the load word and the RD and the RS1 and immediate. So you know the load instruction generates the target address using RS1 and immediate data, like the RS1 plus immediate. And then you need to know that immediate number is the signed number, right? So as you can see, we can calculate the address of the load instruction like this. So this R represents the register, and then RS1 is the index number of the register. So register number, then plus immediate. So this becomes the address of the target address of load instruction. And then it's same to the store instruction. But if you see the store instruction, the direction is opposite. So the store instruction reads data from register file with the RS2. Okay, so you can find that the store instruction reads data from register file indexed by RS2, right? And then this is the target. Target of the store instruction is the main memory. So we need to actually store instruction. Store instruction needs to calculate the target address, and then when the target address is calculated, store instruction uses RS1 plus immediate. Okay, so if you see the format of the store instruction, then you need to remember that store instruction, the format of the store instruction, the store RS2, RS1, and immediate. Okay. So it was changed. It was fixed. Okay. So okay. So in the previous class, so we learned about some logical instructions. Also, we learned about some other formats of the RISC-V instructions. So where is the story? Okay. Also, we learned how the program, how the binary programs are executed in a computer system. Actually, you need to understand this. It's very important. So I explained that instructions are also kind of data. So which means that this data, the instruction data is also stored in the main memory, like other normal data. What are normal data? Like the numbers, text data, and then but you can say that video or some image data are also some kind of normal data. Okay, right? So our application with data from main memory, then application actually the application of the computer system process the data in the main memory and then generate the result data. That's it. So normal data means that it's some numbers or some text data or image data or some video data used by applications. But you need to understand, you need to remember that in a computer systems, instructions. So instructions like M, X1, X2, X3, and then actually these assembly instructions are translated into machine code, right? And the machine code also, we cannot distinguish machine code with other normal data. And then these machine codes are also stored in the main memory. And then I explained that. So in order to access the instructions stored in the main memory, then we need to know the address of target instruction. And then this address of target instruction is called program counter, PC, right? It's very important because using PC processor reads instruction from main memory, and then when these instructions are read, so which is called fetched. If instructions are fetched from memory, then processor can execute fetched instruction. So which means that we need to use program counter to point the target instruction, right? So in the previous class, we briefly learned about branch instruction. So, and then I also explained why we need branch instruction. We frequently use the conditional statement like if else. So based on the condition of some variables, and we change the execution path. And then it's very critical for the general purpose applications, right? So I said a processor needs to support this kind of statement. So which means that a processor needs to support this kind of instruction. This kind of instruction means instructions that can change the execution path in an application, right? So how can you change? These branch instructions change the program counter. Okay. So for example, usually the program counter is an address of instruction. So which means that we can say that, oh, this is the address of the instruction number 1. And then the next instruction is the address 4, is the instruction number 2, 3. And then the address is the 8, and then 12 is the C in hexadecimal. So we can say that these are the address, which means the program counter of target instruction. And then I said that when instructions are executed in a processor, these instructions are actually executed from top to bottom. So from the first instruction to the next instruction, like the next instruction. And then, which means that when an instruction is executed, like when an instruction 1 is executed, then the current PC, current program counter is the 0x0000. Okay, so current PC points the target instruction, and the next cycle of processor execute the next instruction, the instruction number 2. Instruction number 2 is the next instruction. Then PC is the 0x0004, right? Because the PC of the next instruction is the 2. Then the next clock, the instruction 3 will be executed. And in this case, the PC will be 0x008. Okay. So then when I explain about the branch instruction, then branch instruction change the execution path of the one application, which means that like if A equal B, then C equal A plus B, or as C equal A minus B. And then I explained that these are equal instructions, right? C equal A plus B. Then we need to use add instruction, and then C equal A minus B. Then we need to use sub instruction. So in this case, based on this condition, the target instructions are changing. Okay. And then I also explained that instructions are data, which means these instructions like C equal A plus B, like this is the add. This instruction is stored in a main memory. Also, C equal A minus B, this is the sub instruction. This instruction is also stored in the main memory, but with different address. So which means that different program counter. So for example, if the program counter, the address of this instruction is 0x000C, and then let us assume that the PC of this this instruction is 0x0010. So when a branch instruction is executed, so based on the condition, so if condition is true, then we need to execute this instruction. So which means that and the branch, so this is the branch instruction, and then as I explained, B means represent the branch, EQ represent equal. So which means that this branch instruction check equality between RS1 and RS2. And then if this equality check is true, then jump to L1. Okay, so which means if A equal B, so we check the condition of the A and B, and then if this condition is true, then branch change the target PC. The next PC to the PC program counter of C equal A plus B. Okay, so branch change the next PC. So usually the next PC is the current PC plus 4. Why? So usually the board. Okay. Okay. So I said that usually the next PC, the program counter of the next instruction is the current PC is a program counter of the current instruction plus 4. Why? Why 4? So right. It is because the size of a normal RISC-V instruction is 32 bit, which means each 4 bytes. So it means if the instruction 1, if this is first instruction, if this instruction 1 is stored in the main memory, this instruction occupies 4 byte space of the main memory. Then the next instruction, instruction number 2, will be, so if this is the current PC, then because this instruction occupies 4 bytes of main memory space, then the PC of the instruction 2 should be PC plus 4. So if an instruction is executing from top to bottom sequentially, step by step, then usually the next PC is the current PC plus 4. Okay, so which means that a processor increases the program counter for the next instruction in every cycle. Okay, so if the current PC is the 0x0000, then in the next cycle, the next PC becomes the 0004 and 8, like this. But when the branch instruction is executed, like BQ, then I said that branch instruction changes the next program counter. Okay, so which means instead of using current PC plus 4, so instead of using current PC plus 4 as the next PC, and the branch instruction can change the next PC as the L1, the target of the branch. Okay, so it's L1 represents the target of a branch instruction. Okay, let's see the example. So this is the example code, the example C code that execute the if statement. As you can see, it's very simple. Actually, it's the same to my example. So it check the I equal J, and then if the I is the same to the J, then same to J, then this statement execute the add, and then else, then this C code execute G minus H. Okay. If this is the C code, okay, I believe you can understand the behavior of this C code. Okay. And then when this C code is translated into RISC-V assembly instruction, then you can find that, oh, it's a BNE, not equal. Not equal. So check the X22 and X23. And then it also assume that I is in the X22, and this is the J. Okay, J is stored in the X23. And we use BNE. Okay, so which means that this is the branch instruction, and then condition is not equal. Okay, so which means that if I is not equal to J, and you can find that as here. And where is else? Else is here. Okay, so this else is called the label. Okay, label. So which means if the branch instruction, the condition of branch instruction is true, and then you can find the label here, then branch jump to this label. So which means that branch change the, if the condition is true, the branch change the next PC is equal to the PC for else. Okay, so PC for this instruction. So you can find that after this label else, then you can find sub instruction here. So which means that else represents the program counter of sub instruction. Okay. Okay. So if the branch is true, the next PC becomes the program counter for this label, so which means program counter for sub instruction, right? Because you can find at the else label, you can find sub instruction. Okay, so let's see this. Then let's see the meaning of this branch instruction. So we check the I is not equal to j. If I is not equal to j, then jump to else. So which means this one. Okay. So here, right? So actually you can find this if statement check the I equal j, but when this statement is translated, then we can use the B and E, not BQ. Then if we check the inequality of x22 between x22 and x23, and if two registers are not equal, then jump to else. And then if PC is changed to the PC of this else label, then a processor will execute sub instruction, right? Then exit. Then, if the condition is not true, which means it's false, what will happen? If the condition is false, the branch will not be executed. So which means that PC will not be else, right? Which means I said that in the normal case, the next PC is the current PC plus 4. This is the normal case. And then if the branch is not true, which means the next PC becomes the current PC plus 4, right? Which means next instruction. What is the next instruction? The next instruction is the add instruction. So you need to understand the behavior of branch instruction. So if the condition of a branch instruction is false, right, then the next instruction, the very next instruction will be executed. Otherwise, if the condition of a branch is true, then the PC is changed to the target of a branch instruction. So then we need to find the target of a branch instruction here. Then the instruction, the target of the branch will be executed, right? So if you see this code after the add instruction, also you can find the PQ, X0, X0, and exit. What does that mean? So this PQ just compares X0 and X0, and then we know that X0 is the 0 register, so which is actually always 0. The result of X0 is always 0. And then, this is the branch instruction, and then condition is equality. So we need to check the equality of X0 and X0, which is always true. So this is actually unconditional branch because we just compare X0 and X0. Okay, so it always jumps to exit. Okay, then also you can find some other instructions here, but this is not important in this case. So actually it jumps to the exit. So what does that mean? Based on the condition of I and j, then this code can execute add instruction here, like here, it's the 1. Or this code can execute the sub instruction here. Okay? That's how branch instructions are working in the processor. Okay? I hope you can understand this code. So this is another example. So if you see this example, then this is the Y statement. So what does Y statement mean in this in the C code? So this is the condition of a Y statement, and then if its condition is true, then Y statement execute this statement I equal I plus 1 repeatedly. Okay, so this is the meaning of Y statement in C. So let's see. So this is the actually iterative loop. So which means that based on this condition, then this instruction, this statement is repeatedly executed. So, in assembly code, repeatedly executed means that. So you can find branch instruction here. So you can find the label of the target of this BQ is a loop. And where is the loop? The loop label is here. So what does that mean? Repeatedly executed. So which means then PC, instead of jumping to the next instruction, program counter is changed to the program counter of previous instructions. That is the meaning of repeated execution in an assembly code, right? You understand? Right? So you can, as you can see, you can find the branch instruction here, and then the target of the branch instruction here, and then as you can see, it is changed to the previous instruction. Okay, that's how the iterative loop is implemented in assembly instructions, assembly code. So if you see this code, then you can find that I is x22, and then K, there is K is here, K is in x24, and then address of save. So this is the base address. The address of save is in x25. Okay. So then how can we calculate the address of save I? So this is the base address. The base address of save, array save. And then how can we calculate the address? Address of save I. And then let us assume that so this is the word, actually the size of a single element is 4 bytes. Okay, which means it's a kind of integer or single place is a floating point. But let us assume that the size of the single element is 4 bytes. Okay, then how can you calculate the address of say I? It's address of save 0. So which is the base address plus I multiplied by 4, right? You understand? Because the size of a single element is 4, then so this is the memory, and then this is the save 0, and then save 0 will occupy 4 bytes of memory space, right? And then after that, there will be save 1, okay? The next element of save array. Then the address of save 1 will be address of save 0 plus 4, right? So we can calculate the address of save I as this equation. You understand? Then this is how we calculate the address of save I. So if we see that this assembly code, so I will explain the meaning of this assembly code, and you can find that you can find the load word here. Load word calculate the target address using x10 plus 0, right? So which means that is x10 is the stores the target address of a load instruction. Then how this target address is calculated? So as you can see, if you see the previous instruction, then you can find that SLLI and then add towards the result, x10. Okay, so x10 is used by this load order instruction. Okay. So I is in the x22, this is the SLLI. So SLL is the shift left logically, the SLL, and then this is the immediate, and then this is 2, which is equivalent to the I shift left by 2. Understand? This is equivalent to I multiplied by 4, because this is computers handle binary numbers, right? Shift left by 2 equal to multiply by 4, power of 2. Okay. And then, so base address is in x25 here. And then base address plus, so we already calculate the I multiply by 4 in x10. So x10 plus x25, this is base address. This is I multiply by 4. And then the result is stored in x10. Okay. And then with this x10, the load word access the data, which means load word store the save I to x9. You understand? Then check the BNE and then x9 and x24. So we check the save I. So x9 has the save I, and then we check the equality between save I and k. Okay, where is k? K is in x24. Then if it is not equal, then jump to exit. Okay, so if the condition is equal, then this instruction is executed, and I x22 x22 1 is executed, then unconditionally jump to the loop, the former instruction. Okay, that's how this while statement is implemented. It's translated into RISC-V assembly code. Do you understand? So I hope everyone can understand this code. So actually, branch instructions are a little bit tricky, because until now we just learned about the arithmetic or memory instructions, but the meaning of arithmetic or memory instructions are very, I think it's easy to understand, right? So just change the operand, the destination of the instruction. But branch instruction is a little bit different, because branch instruction just changes program counter. Okay, that's why a branch instruction is a little bit tricky to understand. Okay, but I hope you can you read this code, like this is the if statement. Also, you can. I hope you read with this code also. This is the iterative loop. Okay, and then so I will explain about the basic block. Actually, the basic block is also very important concept in a program code or program instruction. So what is the basic block? So this is the definition of basic block. Okay. A basic block is a sequence of instructions. So this is the group of instructions, but this group of instructions include no embedded branches except at end of a basic block. So what does that mean? So if you see this code, you can find two branch instructions. So if the branch instruction is in the middle of a base, this sequence of the code, sequence of instructions, then we cannot say, oh, this is a base block. So no embedded branches except at the end represent actually this can be a base block, but you can find that inside of this base block we cannot find any branch instruction except at the last instruction of the base block. So at the end of the base block. So in the base block you can find a branch instruction only at the end of base block. But in the middle of a base block, we cannot find any branch instruction. So what does that mean? In the base block, if this instruction is executed, and then in the next clock, we guarantee that very next instruction will be executed. Do you understand? So in a base block, the branch instruction is located at the end of the base block. So this is the last instruction in the base block. So which means that if this instruction, like SLNR, is executed, and then with 100%, then next instruction, very next instruction, add instruction will be executed. Well, it's obvious because we cannot find any branch instruction here, except at the end of the base block. And then another condition is the no branch target, except at beginning. So, which means you can find this is the target of a branch. So if an instruction is labeled by a certain label, like loop here, then this instruction can be a target of branch instructions, right? And then the definition of the basic block is that no embedded branches except at the end, and then no branch targets except at beginning. Okay. So which means in the basic block, if the first instruction is executed, then with the 100%, next instructions are executed sequentially without change of execution path. That is the meaning of a basic block. So in this example, this is a basic block. Why? Find the definition. So this is the first instruction. Then we can find only the target of the branch, the loop, at the first instruction of the basic block. And also inside of this basic block, we cannot find any branch instruction except at the end of the basic block. So this is the basic block. Then why is it important? Why do I explain this? It is because the size of the base block is critical for the performance of applications, the performance of computer systems. So actually, we will learn about the process architecture in chapter 4. Chapter 4, and you can know that why the basic block is critical for the performance of a computer system. But just to also in this chapter, just to remember that the performance of an application or performance of a computer system, but actually the size of a basic block is critical for the performance of an application. Okay. If the basic block size is large, so which means that if a certain instruction is executed, then many other instructions will be executed sequentially. If the basic block size is large, then we can increase the performance of this application. Otherwise, so on the other hand, if the size of basic block is small, then performance will be low. So this is because in a processor, just remember, in a processor, if instructions are executed sequentially from top to bottom, then performance will be high. Okay. But if the execution have some diverged, the branched execution paths because of branch instruction, then performance will be low. Okay. So we is the reason of this low performance in chapter 4. Okay. But just remember that in a normal application, it's a normal general purpose application, it's a CPU application, the size of basic block is around 4 to 5. It's very, very small actually. Okay, which means that we can observe branch instructions in every 4 and 5 instructions. Okay, so actually the basic block size is very small. It's not good for the performance of the processor. Okay, but just to remember the definition of a basic block. Okay, so you can find the problems regarding basic block. Okay, so actually I believe you can find the second homework. So I posted the second homework on the Blackboard, and then actually this homework covers the chapter 2. Okay, so what we learned in chapter 2. Then you can find some questions regarding basic block. Okay. I hope everyone can understand about the basic block, also the branches. Okay, so let's see some other conditional branching instructions like BLT and BGE. So when you learned about the branch instruction, we just check the equality between two register operands, like the PQ and then P and E. And equality check is actually very simple, right? Because so you know the data in computer systems is a binary data, so which means there is a 1 1 1 1 1 1 1 1 or 0 0 0 0 0 0 1 1. Then how can you check the equality? You can check the equality of this binary data by checking the equality of each bit. Okay, and then it's very simple because we can use exclusive OR gate. Okay, what is the exclusive OR gate? It's A, B, C is 0 0 1 0 0 1 1 1. And the output of exclusive OR becomes if the A, B are both zeros or ones, then it's 0. And then if the A and B are different, it becomes 1 1. So for checking the equality of two operands, then we can use simply exclusive OR gate. Okay, but we can find other conditional branch instructions like BLT and then BGE. BLT is means the less than, and then BGE represent greater than or equal. What does that mean? Less than represent this operator, right, in C code, and then BGE represent this operator, right? Greater than or equal. So BLT and BGE just check the magnitude of two source registers, the data in two source registers, and then check the condition, like less than or greater than or equal. So we check this operator or this operator. Then for this BLT and BGE, we need to consider the signed and unsigned data. Right. So in chapter 2, we learn a computer systems. A computer system can handle signed data or unsigned data, right? In the signed data, the first one that is the MSB represents the signed bit, and then the unsigned data, MSB also represents the magnitude of this digit. So actually, when you use BLT and BGE, then we need to consider the data type of the source registers. Okay, so this is the example. So actually, it's the 64-bit data. But so if we just compare the X22 and X23, and then if these numbers are signed number, then X22 is actually the all ones, which is it's -1, and X22, 23 is the 1. So if we just check the magnitude of the X22 and X23, then we already know that +1 is greater than -1, right? So if we use the signed number for comparison, then the result is the X23 is greater than X22. But if these numbers are unsigned number, it's a very large number, right? So all ones. So actually X22 is greater than X23. Okay. So a processor needs to distinguish these cases. So actually, if we use the normal BLT and BGE, then we assume that the operands, the register operands include signed number. Okay, so if we just use the normal BLT and BGE instructions, then we assume that the registers include signed data. Okay, so actually the default data type is the signed data. But if we use the BLTU, the U represents the signed. So here, then is branch instructions compare unsigned numbers. Okay, so you can just remember that the default data type is the signed data. Okay, so if there is no U, then these instructions just handle signed data. Also, you can find that the immediate numbers are signed numbers. Okay, but if we just add U postfix at ELTU or BGU, also LBU and LHU, then these instructions handle unsigned data. Okay, we need to distinguish two different cases. Do you understand? Yes. Okay. The next topic is a little bit tricky topic. It's a little bit tricky. Because the next topic, I will explain about the procedures. And what are procedures? Actually, you can think that these are functions in high-level languages. What are functions? We frequently use functions in our program code, right? Like, so this is the foo function, foo int a comma int b. So this is the function name. This is the function name, and then function receives argument. So it's the input variables. So those are called arguments. And then function returns some result. Like this is the result type. So like the C equal A plus B, and then return C. So this is the typical example of a function. So function is some independent, so it's some grouped instructions, and then actually we frequently use function because we don't want repeatedly write the same statement in our code. So if we use the function, then if this group of statements are repeatedly executed, then we can just replace each statement with function. Okay. Actually, you can understand that procedures. Procedures are functions in a program code, high-level language. Okay. So then a processor also needs to support procedures like functions. How? Let's see how this function is executed in a normal program. Okay, so it's a C program, like then when a function, so int a comma b comma c, okay, is a variable, and then c equal, when a function is called, then we just use the function name here, and then we give arguments, the input variables to the arguments of a function. Okay, then the function is here, and then also you can find some next instruction here, like next instruction statement here. So let's see how function is executed in this statement. So you can find that, oh, this is some instructions. So instructions of actually it's a parent function, but so you can find some instructions. Okay. And some variables are given to a function as arguments of a function. The function is called. So called. Okay. So when a function is called, this statement inside of a function definition are executed. Do you understand? So instead of this function name, a program executes this statement, the statement inside of a function. Then see, this is the return value. The function execution completes, function returns this return value to the parent function. So C becomes the output of the function, and then the next instructions are executed. Okay, so when a program is executed, statement, so instructions of the program are executed sequentially. Then when this program encounters a function call, then these instructions are executed, and then when function execution completes, then the next statement are executed. So why do I explain like this? We just understand that these are instructions, okay? Instructions are data, and then also function code includes instructions, right? So these instructions. And after that, also we can find the instructions of this parent function, the main function. Then how can you support functions? The function is called, these instructions are executed, so which means that we need jump. We need jump to the program counter of these instructions. You understand? So when a function is called, instructions inside of this function will be executed. So which means that the programs are executed like this sequentially. And this program encounters function call, and the function is function call, and the function call is executed. Then we need to execute these instructions, which means PC is changed to the program counter of these instructions. Okay, and then function, the instruction inside of a function is executed, and then after that you can find return, which means that after this function call, we need to return to the parent function. So okay, then these instructions are executed sequentially. So which means return is also jump. So which means change the program counter to the program counter of these instructions. Okay, you understand? That's how functions are executed, and that's how procedures are executed in a program. Okay, then in order to support the procedure calls, processor also support the instructions for these procedure calls, and then as I mentioned, processors support jump instruction. And actually this jump instruction is similar to the unconditional branch. So it is because when the program is executed like this, and program just encounters function call, then unconditionally program jumps to the instructions inside of a function. Okay, which means we just change the program counter to the program counter of these instructions, which is the unconditional branch. So, and then this is actually jump. So this file also supports the jump instruction, which is actually unconditional branch instruction. Then, so this is how the jumps procedures are executed, and then actually I already explained these steps. Okay. So then also unit, but I explained that main instructions in the main function are executed sequentially, and then we just encounter function code here, and then if the function completes, then we need to execute the next instructions. Okay, so actually we can understand like this. These are instructions in a function foo. These are instructions of a main function, and then this is the full function code. Then also you can find some other instructions. Okay. First, the required operate behavior is the jump. Okay, so which means that this is the PC of the function instruction. So we need to jump to the program counter of the first instruction of this function. Okay, and then another required behavior is the actually this direction. This is the return. Okay. So when the return is executed, then processor needs to execute the very next instruction of a function call. Do you understand? So which means in order to jump to the function by function call, then we need to use the program counter of the first instruction in function or procedure in a function. And at the function call, we need to return to a parent function. So I said return. And then for this return, we need to know program counter of the very next instruction. Do you understand? So in order to return to a parent function, so we need to remember the return point, right? In order to jump to a function, some other place, then we need to know the address of the other places, right? But we need to return to a parent function. The parent position, the original position. So which means we need to also store the return point. And what is the return point? Very next instruction of the function call. Okay. So just remember, the function is not support the function, and RISC-V, actually most of the processor support unconditional jump. But for this unconditional jump, then we need to also store the return PC, the return address. Okay. So in order to support the function call, RISC-V supports the two different instructions. So the first instruction is the JAL X1, and then this is the label. So the meaning of JAL is the jump and link. So, and then this JAL is used for the function call. The function call means that we jump to the first instruction of a jump function. Okay, it's a function call. Then what is required? So in order to jump to a target, that is the first instruction of the function, then we need to know the target address, target PC of the function. And we need to store the return point. Okay, because when a function call is complete, then we need to return to a parent function. Okay, the return address is stored in the RD. So format of the JAL is the JAL, RD, and label. So this label is the target of the jump instruction, target of the jump here. And then this target becomes the first instruction of a function. And then the RD PC plus 4. I said the return point is the very next instruction of the function call. So it's the next instruction actually. So actually JAL is the function call. This is the function call. So and then when a function completes, then we need to return to the next instruction. So what is the next instruction? Next instruction will be here. The very next of the JAL. So when the JAL is executed, the PC of the next instruction. So this PC of the next instruction is the PC of JAL plus 4. Okay. So that is the meaning of JAL. Okay. Then also the RISC-V also needs to support return. So return means that, so actually using JAL, we store the return PC in the RD. So actually we use X1, the first register, as the return address of our function. But for the return, then we need to update the PC using as the RD of the JAL. So this return address, return PC is stored in RD, usually X1. Then in order to return, then we need to restore this stored PC, the PC stored in RD as the current PC. Okay. So in order to support this return operation, the RISC-V supports the JALR. Okay, the R here. So it's a jump and link register. So JALR also has the destination register. Okay. But, and then JALR reads the data from this RS1, the source register 1, and then so it's actually the RS1 RS1 plus this is the immediate value. This is the immediate. Okay. So this is the meaning of JALR. Okay. So if you see the I refer to I here, then you can find that it's so small. You can find the JAL and then JALR here. Okay. So you can find the meaning of the jump and link. So here, the RD and the PC is the PC plus immediate can be 0. Okay, and then also you can find the meaning of the JALR here, the jump and link. So you can find the meaning of JALR here. Okay. Okay. So I think I need to stop here. So this is actually examples. What I think I need to explain about the example of a function code next class. But just remember this procedure. The required steps for function code or procedure code. Okay, and then so just remember these steps. So just remember these steps I explained for the function code. And then I hope in the next class I will cover the example of function calls. Actually, this is a little bit tricky part in chapter 2. Actually, I think this is the most difficult part in chapter 2. Actually, the function call parts. Okay, but it's very important. So. And actually, in the next class, I will explain about the function call with examples. Okay. Okay. So I will stop here. Any questions? Then, as I mentioned, I posted the second homework assignment on the blackboard. Okay. And then actually, please type the homework problems by yourself. So it will be very helpful. Okay. Okay. Thank you for your attention. And then see you in the next class. 감사합니다.